Welcome to This Explainer. Today, we're taking an awesome practical tutorial by Sana Hassan from Tech Post, and we're going to transform it into a roadmap. We're going from basic local AI inference all the way to advanced hardware-aware cloud deployment using the Qualcomm AI Hub. If you've ever wondered how to bridge that massive gap between testing a model locally in PyTorch and getting it running efficiently on actual physical hardware, well, you're exactly in the right place.
So here's our roadmap for today. We'll be leveling up your skills across 5 key stages. We're going to set up the AI workspace, format and load our models, run some local inference, step it up with object detection using YOLOv7, and finally deploy straight to cloud device hardware. Let's get into it. All right, level 1, setting up the AI workspace. Before we can do any of the cool AI magic, we gotta prep our canvas. We'll start by installing the core QAI Hub models package right inside Colab, and we'll set up an output directory to keep all our generated files nice and organized. But honestly, the most crucial step here, disabling gradient tracking. Since we're strictly optimizing for inference, meaning just running the model to get predictions, not training it, shutting that off saves a massive amount of memory and just hugely speeds up execution. Next up, we need to tackle a pretty crucial translation step to avoid those incredibly frustrating input shape errors. In computer vision, standard image tensors usually put the color channel last. That's the NHWC format. But our Qualcomm AI model, it expects NCHW, where the channel comes first. It's kind of like speaking two different dialects. So we just build a quick to NCHW function to act as our universal translator. Trust me, it saves us from a lot of headache-inducing shape mismatches down the line. Moving right along to level 2, formatting and loading models. Now that the workspace is good to go, let's bring in the brains of the operation. First, we query the hub to see what model packages are actually available to us. We're going to load up MobileNet-V2, which is just absolutely fantastic for classification. But before we even use it, we have to read its instruction manual, basically, the input specifications, so we know exactly what it's expecting to see. Finally, we prep our ImageNet labels. That gives our AI the actual vocabulary it needs to tell us what it's looking at. Now, AI models naturally output these raw, dense, mathematical scores called logits. To make sure our results are actually human-readable rather than just a massive wall of math, we define a handy little helper function called top5. By wrapping our output in this function, we're completely transforming those heavy, unnormalized numbers into a clean, prioritized list of the top 5 most likely objects in our image. Okay, level 3, running local AI inference. The pieces are in place, so let's actually test if this setup works. We're going to test the waters twice here. Initially, we'll use the super safe, built-in sample input, patching it right through our translation function. That guarantees our core pipeline is completely intact. Once we verify that's working seamlessly, we level up. We grab a random, real photograph from the internet and throw it at MobileNet-V2 to see how the model handles itself out in the wild. But look, as we all know, real-world data is messy. So before the model ever lays eyes on that real photograph, we have to rapidly run it through a few mundane but absolutely vital prep steps. We're talking standard resizing, cropping it down to the exact dimensions the model was originally trained on, and converting that raw pixel data into a PyTorch tensor. Honestly, this is the secret sauce to actually getting accurate predictions. All right, on to level 4, object detection with YOLOv7. We are stepping it up from simply asking what is in an image to pinpointing exactly where it is. To speed our workflow up, we create a reusable run demo function to handle official command line demos. We give the MobileNet demo a quick spin, and then we pivot. We install the specific extras needed for YOLOv7, run the new detection demo, and then visualize it. This lets us literally see the generated bounding boxes drawn perfectly around our detected objects. And now for the grand finale, level 5, cloud device hardware deployment. This is where we take everything we've built locally and push it to actual physical hardware. Once we configure our API token, we unlock this seriously incredible sequence. We trace our PyTorch code to lock in its computational graph, compile it down into a highly efficient TFL-Lite format, and then, here's the coolest part, we profile it on a real physical Qualcomm device in the cloud. We're no longer just running on generic servers, we're submitting the inference job to targeted silicon to get actual true performance metrics. Just take a look at the massive leap we've made here. Local PyTorch inference is great. It runs right in your workspace and uses native code for basic software testing. But cloud device deployment, that takes your logic, compiles it specifically for mobile architecture via TF-Lite, and gives you real hardware-aware profiling on physical Qualcomm devices. You get to see exactly how your AI is going to perform on the literal phones your end users are carrying in their pockets. To wrap up our mission, we download the device output back to our workspace, confirm our top printed predictions, and then save that successfully compiled TF-Lite model. The whole round trip is completely finished. We sent our instructions out to the hardware did the heavy lifting, and it handed us back the results along with a perfectly tuned model that is totally ready for your next big project. So, we've successfully journeyed from simple local experimentation all the way to hardware-aware deployment using the Qualcomm AI Hub. You now know exactly how to prep the data, run the inference, and deploy straight to physical silicon. The hard part is done. The only question left is, now that you have these tools at your fingertips, what are you going to build? Thanks so much for joining me on this explainer. I really hope it sparked some exciting ideas for you, and I will catch you in the next one.